Welcome to the class meeting for day 2 of our unit on magnetism. This is only 2 pages, and 4 images, so I may find myself talking a bit off of each image, I suppose. I'm going to start with a problem from the practice set for day 1. This was one that was missed by a lot of people. Admittedly, I did say that you just needed to, let's see. Oh, I didn't clip the whole thing here. But basically, we didn't use compasses in class because we're not meeting. So if we were starting this unit in the classroom, we'd have had small compasses, and we would have walked around the classroom and noted the direction of the needle. Generally, a compass needle will always point north. And so I'm giving you 9 locations around Kettle Cove, and I'm giving you the direction in which one of the compasses is pointing. So that should be orienting you to north. So therefore, regardless of where you walk around, I mean, unless there's some huge magnet that you're going to walk by to disturb the compass, all these other compasses should also be pointing in the same direction. And the reason for that is because Earth itself has a magnetic field. Now, interestingly, while we learn in Scouts programs or outdoor programs or whatever that the compass needle points north, from a science standpoint, that is the south pole of the created magnet within the Earth's core. So I think on tonight's practice set, I have you draw the field lines for Earth. And Earth's magnetic field is based on moving molten iron in the core. So it's not exactly like having a huge bar magnet in Earth, and yet to appreciate the field lines is often shown like that. So if we had if we could imagine a big bar magnet in Earth, in order to create these field lines, south would be up top, north would be down below. So that's something like you're going to see in tonight's practice set. And if you allow the Earth's iron molten core to be represented by a bar magnet such as this, then when you draw those field lines, much as you've already done in other contexts, you would see that all those field lines would end up pointing towards this top part of the Earth. And so if you're at Kettle Cove, you're experiencing those field lines, and that's why your magnet always points towards the north. Okay. Then in the practice set for tonight, I'm returning a little bit to fundamental magnets study. And I like this question. This would clearly be on your assessment because it's easy for me to write. I can swap the poles on this magnet here. I can swap the poles on this magnet here. But basically, the problem is similar in that you have a fixed magnet here. Perhaps I should have said that in my image. This is a fixed magnet, and this one has a pivot point. So it can rotate, we might say, to the left, or we can rotate it to the right. And I've used the terms clockwise and counterclockwise. So if you think that when this system is allowed to move, that the North Pole would swing up here, then your answer is going to be clockwise rotation. If you think that the South Pole would swing this way, then your answer is going to be counterclockwise notation. And so what happens is opposite poles attract. So where this magnet is fixed and this one can swing, you're going to see a counterclockwise rotation, and that South Pole is going to try to get as close to the North Pole as it can. So you'll see a variety of problems like that, both on the practice set tonight and on the upcoming unit test. Then we start to explore the interaction and the relationship between electricity and magnetism, and it's another one of those things you could study more in depth than what we will do. We're getting our first exposure a couple different ways. So this comes from your book. This is a wire right here. That's a copper wire. Same on the other side. And what these are magnets. And what you're doing is you're placing the magnet at different locations around the copper wire. And what one would notice is if there's no current here, so I think we're losing the caption, which is fine. On this wire on the left, there's no current. So presumably it's hooked up to a battery, but nobody's flipped the switch yet. So we have no current through running through there. And you can see that the compasses are undisturbed. They're all pointing, presumably, to the North Pole on Earth. This one here is, I guess I'll say yes current. So someone here has flipped a switch. So you now have electrons that are flowing through that copper wire, as we have studied before. Well, current generates a magnetic field, which is just awesome, because up until this moment, we've known that magnets create a magnetic field. But here we have moving charge creates a magnetic field, or I should say electric current creates a magnetic field. So that's why all these compasses, they're orienting in a circular pattern around the current carrying wire. So you're going to read a little bit about that. But again, that's one of our experiences with, wow, there's an interaction between electricity and magnetism. And then the FET simulation that I do also allows an example of the interaction between electricity and magnetism. It does so in a slightly different way. So as in your reading, it's mentioning actively turning on a current, by having wire connected to a battery, actively turning on a current and then observing a magnetic field. What this one has you do, this FET simulation, also linked to Classroom, it has you taking a magnet and moving it back and forth around copper wire. So there's no battery here. The flow of charge, or the electric current in the wire, is generated not by the mere presence of the magnet, but by your moving the magnet. That's why I've got the hand here and the moving back and forth here. So what you do in that simulation is you push the magnet in and out, and you'll observe a flow of electricity, which will run the light bulb. So that, again, is a second way of reinforcing the interaction between electricity and magnetism. Now, I'm only at 7 minutes here, so I'm going to talk for just a little bit longer. It's nice to make this connection if it's possible that we can get to it. But how we generate a lot of our electricity as a society is by the action of a generator, which is mechanically coming up with a system for, say, moving magnets around a coil. Or similarly, we could move a coil around a fixed magnet. There are different ways to design it. But if you had, and we haven't studied mechanisms per se where we can create a rotating motion out of the linear motion of water. But if we were to start to look at that interplay, you could appreciate that mechanically it's not too hard to create a system that moves the magnet back and forth, such as this. So then you could take that mechanical energy and it could change form into electrical energy, and you would design that system. So that's fun to look at if we have time and pursue that. But right now we're just wanting students to appreciate that there's a relationship between electricity and magnetism. And this FET simulation indeed does that, because you're moving the magnet in and out of the coil, and then you're seeing how that produces electric current. Okay, so with this and the reading from the book, and I think I have an additional YouTube video, something related to the Earth's magnetic field. That's just more interesting than anything I would necessarily ask you questions on. In the FET simulation, I think you'll be good to do today's practice set. Thank you.